respective group session started. They may be in a illusion that still the break is going on. Don't say regular, you are never regular.
Yeah, let's start with sentiment analysis techniques. So what are the techniques? So what are the different techniques that can be used for sentiment analysis? So we have seen what sentiment analysis and where it can be used, what are the applications and what are the challenges. So now let's see what are the techniques, what techniques can we use for doing this sentiment analysis. So we have different approaches for doing this sentiment analysis, and the approaches we can use are the rule-based approaches, the supervised learning approaches, unsupervised learning approaches, and the deep learning based approaches. Of course, deep learning approaches again could be of supervised and unsupervised in nature, and
ये फोटो भेज दूँगी डिपार्टमेंट जब हेड सर से आपको जब बातें सुनने मिलेगी ना.
So rule-based approaches, if you consider, so you need to write independent rules for every sentiment analysis. So if this word is available in the document, then consider it as a positive. Otherwise consider it as negative. Or if all these set of words are available, so we will be dividing the words into, identifying the keywords, so which are positive and negative. So if these positive words are available and these many positive are available, then I can say it's a positive, or these many negative are available. So then such kind of algorithm we are drafting. So one rule by rule we are drafting such kind of algorithms. We call them as the rule-based approaches or the heuristic approaches. But the problem with these rule-based approaches is writing the rules exhaustively will be a difficult task. And when you change the training data, again your set of rules need to be changed. Or when your data changes, again the rules need to be changed. That's a problem. So again, the person who started developing the algorithm, if he leaves the organization, then it will be a problem. So these are all the problems or the limitations with the rule-based approaches. So that is where the machine learning algorithms are much more helpful. So, and the machine learning algorithms could be of supervised and unsupervised in nature. And under supervised learning techniques, you must have the training data, which is having some labeled data, some unlabeled data, and depending on the levels. So if you are going for the aspect level, then you do the topic modeling. Otherwise, you have to have different levels of sentiments and all. So then the training you are using the training data and you are using the machine learning algorithms such as SVM or maybe a neural network algorithm, or you can use a KNN algorithm, or for the text you can use a naive-Bayes algorithm. So these are the algorithms you can use under the supervised machine learning algorithms. And unsupervised machine learning algorithms, maybe I don't have labels. So I am just started developing the application and I don't have any training data. Then, so is it not like you cannot apply any machine learning algorithm? Is of course still you can apply. What you can do is you have to group the data. So like what is clustering? So like you are grouping similar entities. That's what the clustering, right? So use a clustering based approach, cluster the data, cluster all your reviews or the text documents you have, and then like assign each group into one of the sentiment. So that is how you can apply the unsupervised learning algorithms. Or otherwise the recent successful algorithms are the deep learning algorithms. So either you use a deep neural network algorithms, or you can use the convolutional neural network algorithms, or you can even use the RNN based, the recurrent neural network based algorithms. Any of these algorithms you can use, or otherwise you can even use the transformer based approaches, which are the self-attention based algorithms. So any of these algorithms can be used. So maybe in the due course I'll explain shortly each of them. So then what is a pipeline? What are the various stages of the sentiment analysis? So of course whenever we start working on sentiment analysis, you have to first do the data collection and pre-processing, because text, right? And when you would like to do something with the data, so everything is about the data only. Unless you have the data, you cannot do anything here. So then you have to collect the data. Whether you can collect the data from different resources and all. Once you have the data, you may need to apply the pre-processing, then you have to do the feature extraction, then you have to do the model training and evaluation. Yeah, coming to the data acquisition. So what is data acquisition? So collection of the data is known as the data acquisition. And so whether you there are again different cases that need to be considered. So maybe if the data is already available, then the data could be available in your local machine. Then you can directly run your machine learning models, or you can apply the pre-processing and do it. Or otherwise, if the data is available in your server or in the database, then you have to load your data into your local machine, and then you have to do the things. And And maybe if your data is like huge amounts of data which is available in cloud, then how can I partition the data and then download the data and then work on that? So that kind of distributed computing algorithms you need to think about. And if less data is available, then what do you need to do? So if sufficient data is available, maybe that is okay, directly you can work. So if huge amounts of data, then again, so data should be partitioned and then you need to work on that. Or otherwise, if insufficient data is available, then you have to go for the data augmentation and then you have to use synonyms and then create new data. So that is how you can generate new data, or you can use the back translations and all. So that is maybe, so I have like English data and I have corresponding translation. I can do the translation then back translate it to English. So then such kind of algorithms you can use for generating the new data. And maybe if the data is available, then you can use those approaches. If the data is not available, then what do you need to do? So if the data is not available in your local machine or with you, then maybe you have to rely upon some other external sources. Maybe I would like to work on the COVID-19 related data. Then what do I need to do? So it is available in some other website. So then, so such kind of website I need to use, and I need to download the extract the data first of all. Maybe I can use the web APIs such as or beautiful soup kind of algorithms I have to use for extracting the data. So then I have to clean and then I have to work on that. Or otherwise data is not at all available. So if the data is not available, then you cannot do anything anyhow, right? So data should be available, but to what level it is available, and so at different levels what kind of approaches you need to follow, that we need to decide upon. So then we have text pre-processing. So once you have the data, so it is very much important for us to do the text pre-processing of the data. So why do we need to have the pre-processing? So you need to clean the data. Why? Because say for example you are extracting the data from other website, or maybe tweet analysis. So I would like to do the sentiment analysis on the tweets, so which are extracted from Twitter, or some tweets some reviews extracted from Amazon or Flipkart. So then straight away I cannot use that. Why? Because maybe it is including some emojis also. While we are doing the tweets, we can do the emojis also, or hashtags or also should be there, must be there. Then how do I directly pass those? I cannot use them for for the modals. Then you need to do some cleaning. So text cleaning is important. So you have to remove the HTML tags when you are extracting the data from other web APIs. So such as beautiful soup kind of algorithms you are using for extracting the data. And maybe how to use the emojis, or otherwise maybe spelling, or how to correct the spellings, or otherwise, so if it is good, we don't, maybe sometimes we write it as GD only, we don't write it as good. So then how do we validate that kind of words? So that is where cleaning is very, very important. And then we can do the basic pre-processing. So under pre-processing, so maybe I can divide the entire data into words or sentences, then sentence level or the word level pre-processing I need to do, or otherwise, so if you consider the entire corpus of data, it goes huge, especially in sentiment analysis. So when you consider sentiment analysis, mostly adjectives are very, very important, right? It is good, great, such kind of words, such kind of adjectives plays a major role in the sentiment analysis task, right? And in that task, so if you consider stop words, what are stop words? Stop words are the words which are used for connecting words or the pronouns, something like the, a, and, is, are, will, so something like, so related to the tenses and all. So all these words are known as the sentence stop words. So the stop word removal should be done, so under the basic pre-processing. So you can do the tokenization and you can do the stop word removal, and maybe if there are any reasons, maybe if it is not required, you can remove that also. And so different cases, when you are having different cases, that will be considered as different word in your tokenization process. And in that case, your vocabulary will grow. So that is where maybe you can remove all the cases, so make the data as case insensitive, so that your number of words in your vocabulary will not grow. Or otherwise, in some cases, I would like to retain the uppercase letters. Maybe I am referring to an organization or acronym. So then in that case, I need to retain that. So whether you need to use that or whether you need to remove that you need to take a decision upon. So depending on that, you have to do the basic pre-processing of the data. Or otherwise, maybe the next level of data processing, data pre-processing I need to do. So where I need to do the POS tagging, that is a parts of speech tagging. So whether the word is related to the verb or subject or adjective, adverb. So especially in sentiment analysis, it is very, very important for us to understand, so which are adjectives, adverbs, because they play a major role in deciding whether the review is positive or negative, what is the polarity of the people. So that is where POS tagging or named entity recognition is important, or otherwise co-referencing resolution is also required. So this kind of, we have discussed, right, what co-referencing is. So can we resolve such kind of co-referencing problem? So these are all the advanced pre-processing techniques that we may need to, that you need to, decide whether we would like to do or not. That is what we need to do. I am just showing some of the, pre-processing challenges. When we are doing the pre-processing, what are the challenges that we need to face, we'll be facing. So consider this like a review. I don't like this movie. So usually what we do is we remove the stop words, right, while doing the pre-processing stage. So did not. So maybe we can divide the first sentence into I did not like this movie. These are all the different tokens. And when I do the token stop word removal, so did, I will go off and did will be removed, not will be removed. So but like, moving, those two words will be remaining, right? So but the problem here is that not is very, very important. So it gives lot of value addition to my sentence. So in whether it is positive review or negative review, the first sentence, I did not like this movie. That's a negative review. And whereas the second one is I really like this movie, it's a positive review. Right? So when I do the stop word removal from the first sentence, so did, not, I, all these words will be removed. Then only the words like and movie will remain. So then in that case, I will be losing important information. So whether I need to retain all the words in my reviews, in my text, or so whether I need to remove the words. So that is what we need to take a decision upon. So in this case, at least we need to retain all the words. Or otherwise, when there are negations in the sentences, one simple thing what we can do is, so starting from the word not, wherever you the occurrence of not started, so you just append the word not to all the words. So till you come across the punctuation later in the sentence. So you can see here the next word is did not like this movie, comma, but I, right? There is a punctuation after movie. So actually when we do the stop word removal, but and not will be, sorry, did and not will be removed. So like, movie, they will be retained. But what we do, so instead of instead of stopping the stop word removal and instead of losing the information, what we can do is the not will be attached with every word after the not. You can see, so how the words are now before we do the tokenization process or stop word removal. So we are doing this. So whenever we come across the negative words, the not kind of words, so not underscore like, that brings the negativity. So even if you apply the stop word removal, the did will be removed, not will be removed, but still the negativity is still remaining in our text. So we are making sure that that's very, very important when we are doing the sentiment analysis or when we are working with the text, right? So this kind of pre-processing, we should be careful while doing the pre-processing. And then when we are analyzing the tweets, so maybe I have downloaded the Twitter tweets, so and then I would like to work with that. So what are the challenges I face before I start doing the modeling? So modeling comes later, right? So before doing the modeling part, so we have to do all the data collection is done. So then the pre-processing is very, very important. So when I collect the reviews, collect the tweets, then you can see it's like the data is unstructured. Of course, it could it could contain some emojis or it could contain some elongated words. So you can see I'm showing some example. So usually we write it, when we like it, we write it as too good, something like that, right? So G, O is extended. But the actual word is good only. But that kind of word is not available in dictionary. But because of that, you should not remove such words. That is important for my review, right? So that kind of words, how to handle that. And the noise, if it is having some noisy data. And also spelling variations could be there. So instead of writing grade, what we write, so we could write, some people could write it as GRT or GR8 also they could write. So how to handle all these? So these are all the challenges when we download the data from Twitter. Or it could have something like hashtags. So whether you need to consider that or remove that as noisy data. Or maybe usernames. So how I can understand that this tweet is related to Kohli. So but there is nothing like Virat Kohli. So it will be something like the username will be used as @IamKohli. So means it is related to Kohli only. But the word doesn't mean that it's Kohli. It's related to Kohli, right? So it contains the words like Ed, I am. So whether it is related to Kohli or I am Kohli, so that is a great issue to handle. So all these are the challenges that we need to handle before we start applying the sentiment analysis. And one more thing is, so like the length restriction. So in case of Twitter tweets, the length is restricted to 140 characters earlier. So and recently in 2018 or 19, they have extended to 280 characters. And of course they are working on that to make it as, the restriction up to 1000 characters. So that is a length restriction. Then how to handle that? So though there are different reviews, different tweets, they are related to the same context only. Then how to handle that? So all these are the challenges we need to handle. So then in addition to that, maybe tokenization. So after doing the noisy data removal and all, so then we need to handle the tokenization part. So after as part of the pre-processing, we must need to do the tokenization. So what is tokenization? So once we collect the data and we do the noisy removal and or the stop word removal. So then what do we do? So we split the words into text into words or sentences. So depending on the level you are applying your model, whether it's word level or character level or sentence level. So depending on that, you have to do the tokenization. And you can filter the tokens which are unimportant for you, and depending on the tokenization process you are applying, so your dictionary plays a major role. So preparing your dictionary is also important, right? So depending on the dictionary, your vocabulary will be decided. So then the extraction, once we do the tokenization, now these words, so like I have done the stop word removal, I have done the tokenization, everything is done, so pre-processing is done. What is the next stage? So data collection is the first stage and then pre-processing. So once we do the pre-processing, like data collection and pre-processing, then the next stage would be the feature extraction. How do we do the feature extraction? So it's not like the numerical data, right? So unless you have the numerical data, you cannot pass such data to a machine learning or the deep learning algorithms. Then how to convert your text to the numerical format so that they can be accepted by the machine learning models or the deep learning models. So if you consider your CNN or DNN or any algorithm, so for that matter, even if you consider KNN algorithm, so you cannot pass any numerical data to the non-numerical data to the machine learning or the deep learning algorithms. Then how do we convert this data to the numerical data? So that is where your feature extraction, especially when it comes to the text, so feature extraction plays a major role. So then of course we have different techniques. So like we have the bag of word representation, we have the word embeddings, and we have the TF-IDF, term frequency inverse document frequency. This is another approach, and word to vec and the document to vec. So these are the different techniques which can be used for the feature extraction. Even you can use the learned features also. Already there are some pre-trained models like BERT, the language models. From the language models also you can use for extracting the features. Even the transformers you can use for getting the feature. Of course, BERT is a kind of transformer, and recently there is something like universal sentence encoder. So irrespective of the language, you can use the universal sentence encoder to get your data encoded. So that it generates the numerical vectors. Yeah, let's see what is what are bag of words, what are these
previous slide?
Yeah.
Doc to vec. Where did he
Doc.
see?
No, it's doc to vec only. D is not there. It's a typo actually. It's word to vec. So from word you are converting to vector, and doc to vector. Document to vector. So then the bag of words. What is a bag of words concept? So bag of words concept means, so given the sentence, you are going to transform that to the vector. And so we are following the approach, that's what we call it as a bag of words approach. So I have shown some example there. So here you can see, I am just creating some small miniature corpus kind of. There are 3 reviews you can observe. So one is a good movie, not a good movie, did not like. These are the 3. Assume that your data set is having only 3 reviews. So those are the 3 reviews, and now you create your vocabulary. What is vocabulary for your corpus? All the individual words, all unique words of your text, that becomes your vocabulary, right? And from the text, from the corpus, I have created the vocabulary. So that is good. The only unique words we need to consider: good, movie, not, A, good is already there. So we have movie is already there, so we need not to consider. Did, not is already there, like. So these are all the unique words. So with those unique words, I have formulated my vocabulary. So now, formulate a matrix. So here you can observe. So we are converting those sentences. That is the movie reviews. So any text is applicable to any text. That is why I am explaining it. So whatever the text NLP task you are doing, so you can use any of these approaches, the feature extraction approaches, and without applying any feature extraction, you cannot pass directly the text to your models. So now you can see I am formulating a matrix where I will be converting every movie review into a feature vector, numerical feature vector. So now it is every word of your vocabulary is one column. So good, movie, not, from the vocabulary you make columns. So then in the row, so first row indicates the first review. So for the first review, what is the feature vector? So good, movie. What are the words that are present in the first review? Good and movie. So only respective positions. So where the words good and movie are present, in those places, place a 1. And in remaining places, you place 0. So that is how you are getting a vector. Can you see? So it's 1, 1, 0, all zeros. So that is the numerical feature vector. Now my sentence is converted to feature vector. Now I can very well pass it to any of the machine learning model or the the deep learning model, the DNN and all, right? So that is a bag of words representation.
But it suffers with the out of vocabulary while you test.
Of course, yes.
Certain words.
There are a lot of limitations. It's a basic approach, of course we have. That is where we have learned feature approaches. Anyhow, out of vocabulary you cannot handle it. And then we have like the next sentence, you can see, not a good movie. So like that you can convert every sentence into a corresponding feature vector. So this approach we call it as the bag of words approach. But the problem with this bag of words approach is, so depends on your vocabulary. You can see here, so all are discrete features, that's one problem. And at least in this case it's only binary. I am taking only when the word is present or not. I am not even considering the frequency of the words. So maybe how many times a word is present, that I am using, and also so the ordering of information. So are you preserving the order? So the next sentence, if you consider not a good movie. So not is a third word, right? The third word is 1. It's corresponding to the first word of your not a good movie. So there, are you preserving the order of words in your text? But the ordering of the words, order preserving is very, very important, right? That is also lost. So the ordering you are not preserving, and also so like most of the words, most of the positions are zeros if you consider, and if your vocabulary is too large, so usually the typical vocabulary sizes will be 50,000, 70,000, something like that. So in that case, each sentence will be represented. So maybe your typical sizes of your movie reviews will be, if you consider the standard IMDb data set, international movie review database, it will be something like 500 around, or at least 2,000, up to 2,000, but average it is 500. So then in that case, we are actually to represent that 2,000 words. So if I consider the vocabulary size as 50,000, I need to effort to use 50,000, feature vector. So it will be huge. Every sentence is 50,000, right? So unnecessarily we are increasing the dimensionality of the dimensionality of the input. That's the problem. So these are all the problems that comes with the bag of words representation. So one approach you can use is, so you can use the n-gram approaches. So where actually what we have considered was the unigram approach. Every individual word we are taking. So whether the word is appeared in your sentence or not, or text or not, or document or not. So if it is present, then you are placing a 1, otherwise you are placing a 0. So why am I teaching this is like, so if you are working with machine learning algorithms, so better go with the bag of words representation only, or TF-IDF at least. So that is where this will be helpful. So rather than using the unigram, so better consider the bigram approach, where while designing your vocabulary, you are considering bigrams, that is two different words together. So if you consider in the past case, so what was our vocabulary? Good movie. So good and movie together, that forms one bigram. And not A, that will become another bigram. A good, that will become another bigram. So like that, so whichever words are coming together in your corpus, so with that you formulate the bigrams. And you not to confine to bigrams, you can extend that to trigrams, fourgrams, quadgrams and all. So if you are like the n-grams are present, so the corresponding positions will become 1s, otherwise it's 0s. So this is little better when compared to the unigram approach. The accuracy, the scores could be better when you consider the bigram or the n-gram approaches. But still, yeah, I am just showing, so what is the problem? So what is the problem with the bag of words? So here you can see, again the structure has been changed, sorry for that. So now I am just showing another corpus of text and then the pre-processed sentences you can see there. And from the pre-processed sentences, if you formulate this bag of words representation, and we are considering the frequency. So the first, where the cat is present, 2 times the cat is repeated, right? So that is where we are placing a 2 there. So now, it is not continuous, still it is only zeros and ones, like discrete values only. And most of the places it is only zeros. The sparse representation we are getting. These are not continuous. So non-continuous values we are getting. And discrete values. So if you normalize that again, you will be losing some information. So that is the problem with the bag of words approaches. So that is where, can we reduce the size of the feature vector for representing our movie reviews or the text? So that is where another approach was introduced, that is known as the term frequency inverse document frequency. So another better approach that can go well with the machine learning, the conventional machine learning approaches. So what is this term frequency inverse document frequency? So this can be computed using this equation, the mathematical representation of the equation you can see here, the term frequency. So whatever I have shown here is actually a term frequency. So term frequency refers to the value, how many times the word is repeated in your document or the review. That's what the term frequency is. So rather than having the discrete values, so we are going to convert that to the continuous representation. And also rather than having the the sparse representation, we are going to represent the little dense representation. So that is where this TF-IDF representation will be helpful. So here this is a multiplication, so product of the term frequency and the inverse document frequency. So both multiply together, that's what gives you the term frequency and the inverse document frequency. And what is term frequency? We have already seen how to compute the term frequency as a count of how many times a term appeared in your document. That count will be considered as term frequency, and so rather than considering as a discrete value, you just apply a logarithm just to make it a smooth value. So then the inverse document frequency. So inverse document frequency is like you can compute that using n by df. N means the total number of documents and in how many documents this word is appearing, this term is appearing. That is what the DFT is. So you just take the ratio of that gives you the inverse document frequency. And you take a product of the term frequency and the inverse document frequency. And here you can see n by DFT. N is the total number of documents. DFT is the document. How many documents the term is repeated. That's what the DFT is. And of course, to make it smooth, you just apply a logarithm over that. So that is how we get the TF-IDF. So multiply it together. And here you can observe, I am just showing a table where I have like a document words I have taken and the document frequency. So how many times the word is repeated in the document and the inverse document frequency also. Here what you can observe is, so for whatever the words, the frequency is higher in this document, for that the inverse document frequency is 0. Because it appeared in almost all the documents. In that case, I need not to consider that word at all. Do you understand? The physical interpretation we need to understand, not the mathematical interpretation actually. So why we need to ignore such word? Here you can observe sweet. Sweet is appeared 37 times in this document. But still, I need not to consider that. Why? Because the same word is appeared in every document. So while extracting the features, whether you need to extract the discriminative features or the common features, which are important for the classification. Discriminative features, right? So in every document the feature is present, it cannot discriminate. That is why we are ignoring. That is where we are giving the IDF value as 0. When you multiply that TF into IDF, that becomes a 0. That value becomes 0. Right? So that is where we are ignoring such kind of words. And if you consider Romeo, that word is important. So I have taken this from a Shakespeare novel, an example. And the DF is 1. So inverse document frequency is very high. That indicates that, so it is very rare in my documents. And such kind of, so in this document alone, this word is appeared. You understand that? So that is where that kind of features are important for me to, to generate the features which are discriminating in nature. And that is how the TF-IDF it allows you to get the discriminative features. So rather than using the bag of words, that is how these are better.
Can we say that we are in the urge of finding only the rare words which have got impact?
Kind of. Here in TF-IDF we are doing that because the next process is like class discrimination only. So we are kind of extracting the
Can we say like
discriminative features.
any anxiety detections and all can be done by NLP?
Yes.
Whether it will be more benefit using NLP or machine learning?
NLP is what? NLP, the next stage would be machine learning only, right? For prediction anyhow you will be using machine learning models. You will be using all the classification algorithms, any of the classification algorithms, machine learning algorithm for prediction. But the kind of machine learning algorithms are different when you are, maybe something like you are going to use text generation approach.
Like when we apply anxiety for children's.
Okay, you would like to predict that.
Yeah.
Yeah, you can use a machine learning algorithm, but you are working with the text, right? That's where it becomes an NLP algorithm. So, for prediction tasks, you can use a machine learning. What is machine learning? Which allows you to predict something. So, predict a value, maybe the score for the anxiety, that is where the regression algorithm can be used, or otherwise maybe whether the person is having anxiety or not, or to what level, that is where you can use the classification algorithms. Or maybe you would like to group all the anxiety people, that is where the clustering algorithms can be used. But depending on what you are going to do, maybe depending on the words uttered by them, speech is the input. So you need to work with speech first and convert that to the feature vectors. Then you can use the machine learning algorithms. Actually, the stages if you observe.
Did you pass the attendance sheet?
Yeah, I pass that.
Shafana,
I think morning.
Yeah, these are the different stages of your sentiment analysis. So it's not only for the sentiment analysis, this is applicable for any document classification. So yours is also kind of, classification algorithm. So the same kind of stages, right? So data collection and pre-processing is important, then the feature extraction. Once you do that, you can use the machine learning models for model training. Unless it is like generative text generation and all, you can use the regular models. Classification, you need not to have any, recurrent neural networks also you can use, but you can use the regular machine learning models also.
not once, keep that limitations.
This one?
No limitations like that.
Okay. Sure. I think I
Ma'am,
found
we'll
it.
get this all slides.
So sure.
No,
For sure. All
why
this.
this? We will be training a machine learning multiple algorithms with TF-IDF only. So, what factors we should concentrate on, where exactly my performance is not increasing, how quickly it should tap up the TF-IDF as per the literature has proved to be very good. Certain algorithms are proved to be very good.
Maybe especially
A lot of dependency is there on what kind of input data you are giving, because everything depends on that only.
Yes.
Now, as you see, vocabulary size is the factor we have to consider.
Yes.
And those are considering TF-IDF, there also we need to put a capping. What should be the maximum features we should pass to the function?
Problem is if your vocabulary size is high, so your feature vector size will grow.
Yeah, it
The
will
problem.
become sparse matrix.
Yeah, and also the problem is, so if you have the computational resources, then you can afford to have. That depends on the computational resources you have.
This, how to consider that word order, nodes, word order, that other algorithms if we take into consideration like word, some
Yeah, they will consider word order also, right?
window they consider and this thing.
Yes. But the problem, these are all the limitations only, right? Yeah. So did I skip any other slide? Yeah, this is done. So then what are the limitations of TF-IDF? Of course, TF-IDF works well, but still it suffers from some limitations and challenges. So sensitivity to document length. So it depends on the document length. So if your document length grows, what happens is, so like your TF-IDF value, so the score will be reducing. That's the problem. So then vocabulary size. If your vocabulary size grows, again your feature vector size will be increasing. That's again, that problem is not yet solved. That's the problem. And the word order. So we are not considering, nowhere we are considering the word order. So of course what we have done is we have reached a state where we are making the sparse matrix to the continuous level, right? So like the discrete values to the continuous, and also so we are having so the rare words identification, like the discrimination power has been increased. So that's the only thing we have considered in TF-IDF. The other difficulties are still remaining. So difficult to handle the rare terms. So that is the problem. That is like if you avoid that in your vocabulary, then it's a problem. Then sensitivity to scaling, so it cannot scale well because your vocabulary should be limited. So when you increase when your vocabulary grows, your feature vector sizes grows, unless you have huge computational resources, it will be difficult to handle. So then the language dependency, and of course, so it is there for every kind of, so it is common to every, it cannot be common to across all the languages. It should be different for different languages. So that's the problem. And of course, I have talked about the computational complexity. So if you have like huge vocabulary, so huge computational complexity you have to afford. These are all the limitations. So that is where the learned features, that is the word embeddings, have been introduced. So the industry is doing well with NLP. So we are seeing only the real-time applications of NLP only after the deep learning introduction, if you observe. So deep learning actually started to fly from 2012 onwards, and when the computer vision field has seen some glory in the applications, the real-time applications, then people started working for NLP also. So that is where the real-time applications. So maybe if you observe 10 years before, we haven't seen any of the real-time applications of the AI. Is it not? Right? Only in the last 10 years. Why? What is the reason? So one reason is the data, other reason is the computational resources, the other reason is the tools we have, right? These are all the reasons for the growth or the availability of the applications in the real time. So then once the deep learning started growing, then if you observe to your CNN models, when you are working with the computer vision, so maybe you must have studied the computer vision course. So the computer vision, if you are working with computer vision, you can directly pass an image to your model. Is it not? At least CNN you can give directly the images. But is it possible to directly pass a text to our models? No, you cannot. Even if it is deep learning also, you cannot give. What you have to do? Again, you have to convert them into the features, and then only you can pass it. Right? So we have already seen the TF-IDF and the bag of words, they are bad. That bad means your feature vector size grows. So it depends on the vocabulary. The vocabulary size decides your feature vector size. So can we make it like shortened, but still we can extract the essence of the feature vector, like the word. So that is where the learned features came into picture. These are all the word embeddings, which are kind of, we are using the neural network models for designing the feature vectors. So that is what the word embeddings is. So these are the representations.
Sorry to interrupt. This ELMO is basically,
ELMO?
Yes, it is basically focused on the emotional words only, right?
No.
That embedding has got only emotional words, or
No. ELMO is a language model. So how they have trained it is, so they have taken a corpus of text. So they will be giving like a sequence of words. What is the next word? What are language models? So you give the last n-1 words, maybe k-words you give. What is the next word? It has to fit. That is how they train. They train on all the entire Wikipedia and all. The corpus of a large corpus. But this was in 2018. And then came the BERT similarly. And in recent we can see ChatGPT is another transformer model.
no, this model is trained ELMO, and we will be able to use this only their embeddings.
Their embeddings.
And that using that embedding
We can pass it to DNN or transformer or what you call LSTMs.
we can use this embeddings to
Embeddings.
train our machine learning,
Yes.
and we can go with some sort
Yes.
of comparative analysis with what to
The problem is you cannot extract them. So they are embedded as part of the, you can use it. Elmo, anything. Glove also you can use. So unless the tool supports, you cannot use it. That's a problem. So like unless the tool supports, so if you are using Keras or TensorFlow or PyTorch, so they support all these, so they are part of your neural network models. So you can have the embedding layer, right?
If you want to use this particular
Yeah.
model's embedding to where
You can download it. So there will be like Elmo embeddings, GLOW embeddings. So you can download that package and then you can extract the features from it. These are all the learned models which are like kind of pre-trained. So in computer vision you must have observed the pre-trained models.
Yes.
So these are all the pre-trained models. Pre-trained language models. So like LM stands for the language model. Language model. Yeah, you can try that. So GLOW is good, Elmo is like better. Like GLOW is some 2014, right? That's 2008. It's much better. And the flexibility is, so you can use the feature vector starting from 50. The size you can decide. So in GLOW also, there are different, different resources for like files are available, especially with GLOW and all. So global vectors. It is like 50, 100, 150, 300, 600. Like that is how you can decide. So what are these word embeddings? So you are converting every word to a feature vector, and the feature vector need not be like too large. So it is not dependent on your vocabulary anymore. It is dependent on, so like you can decide upon it. So you can have 50 as the size of your feature vector, or 100 or 200 or 300, that depends. And also it's a dense feature vector. There's no more sparse. You're not wasting your computational resources now. It's no more 50,000 feature vector now. It's only 50 or 200 or 300. So that is the reduction you are getting, so that your computational resources will be scaled down to a greater extent. And also, by they are the trained feature vectors, so that how they are trained is, so they learn the context also, and they learn the nearby words meaning also. So when I say bank, whether it's related to the bank or the river bank or the finance bank, so they can understand depending on the context also. So that is how they are trained, the models are trained. So they have the semantic meaning also inherently. And whereas in case of the other models, the bag of words and what is the other one? The TF-IDF, they don't have anything like word ordering. They don't preserve any word ordering, which is very, very important for the text. So image, it is not like, there is no sequence, you need not to preserve any sequence. But when it comes to the text or speech, the sequence preserving is very, very important. So there is structure in the word, right? So I am presenting a lecture. So I cannot say that lecture, present, I am. I cannot say that. It's not meaningful. So ordering of the words is very, very important. So when you consider the order, you have to preserve the order in the features also. So that can be preserved when you are using these kind of word embeddings. The word to back or GLOW or fast text, these are all like GPT. So the GPT we are seeing, of course, it's in different versions. The generative pre-trained transformer. So all these are the trees. BERT is also a transformer model. So like these are all the different kinds of models that you can download and you can use them. The feature vectors you can extract and then use them. And these, I think I don't have.
Ma'am, this last one which is there on GPT,
Yeah.
in GPT 3.5, there are certain models that are treated like ADA model is there.
GPT-4 is also there, but it is not free.
3.5 is only again testing only. So when we are trying to use that, it is not showing that good results when compared to BERT. BERT is only performing well.
GPT 3.5 was a 2018 trained model actually. It's not like recent model. It's a recent model is GPT 4.0, and that they are not giving it for free. You have to subscribe it. It's monthly 2,000. You need to pay to use it. That's the problem. So what the GPT we are using is like it was trained in 2018. So whatever the information it could, so that was available until 2018. Only that information it can. And also, of course, it's not compared to other models. And BERT is also 2018, and it is by Google, right? So Google was leading it. So the performance was also good. That's it. Yeah. So you can see word embeddings. Why do we need to move forward and use word embeddings? Why not the handheld features? So the features like a bag of words or the TF-IDF, we call them as the handheld features. So why? Because manually we are setting the vocabulary size, is it not? And manually we are saying like, so like the TF and IDF we are computing. So that is how they are known as the handheld features. So rather than using that, we are moving forward to the neural network based features. And And when the neural networks are allowed to learn, so they can learn better compared to the other kind of features. And also they are very short, they are dense in nature, there is no sparsity, there are no more zeros. So if you consider the bag of words representation, most of the features you can see, if it is a 50,000 vector, most of them will be zero only, right? So that is a problem, and all the problems have been resolved, and the entire feature vector is a real valued feature, right? And it could have the negative values also, whereas your TF, IDF or your bag of words, they contain only the positive values. So that is where it is taking the advantage, and that is how the word embeddings work much better, and they can preserve the word ordering also. That is how they work much better than the earlier feature representations and for the NLP tasks. That's about that. Of course, I haven't gone through that, because in word embeddings again, for the word to word, we have again the scriptgram approach and the continuous bag of words approach. So how the models are trained is, so it's a language model they have trained. So in case of scriptgram model, so they will be giving like one word and what is the context. So they will be giving while training, so the context they will be giving and it will be learning, and the bottleneck features they will be extracting. So that is how the scriptgram, or otherwise in case of the continuous bag of words, so they will be passing the words, the context, and then so they are expected, the model is expected to learn what is the next word, the language model. So that is how they are extracting better features. So then about the model building, so we are done with the model like data collection, the feature engineering. We are seeing different approaches for the feature engineering, and now comes the model building. And of course we have to use, like when lot of data is available, then so manually doing analysis is not feasible, right? So that is where we better go for the machine learning based predictions. So that is where the model building or the modeling comes into picture. And of course you can use different models. You can use the heuristic approaches where you are using different rules. So you list out the rules and then write your algorithm. So like predicate logic you are using. So that is where the conventional artificial intelligence is. But the problem is, again, so when you change the rule, your algorithm has to be changed. So that's a problem with the heuristic approaches. And that is where we are moving forward, and so the industry started using the machine learning approaches, recognizing the problems with the heuristic approaches. And of course you can use, we already discussed it actually, the supervised and unsupervised approaches. Both you can use. So any of the supervised learning algorithm, like starting from the KNN, the regression, the logistic regression you can use, or the SVM or the naive-based approach algorithm. Any of the algorithm you can use, or the unsupervised clustering also you can use. And of course, the most importantly, the deep learning approaches. You can use any of the DNN algorithm or the recurrent neural networks or the transformers. So any of these models you can use, and which model we have to use, that we need to decide. That depends on the amount of data, the application we are going to solve. So both are the deciding factors when it comes to, so what is the kind of approach. So maybe my problem is very simple, then I better go for the heuristic approach itself. I need not to go for the machine learning algorithm, right? So better if you can list out all the rules for your problem, then why to make it problematic going for the machine learning algorithm. So you can simply list out all the rules and solve your problem. And when you have the training data and your model is like it is not possible to list out the rules, then you have to go for the machine learning algorithms. And you have huge amounts of data, huge computational resources, so then you can go for the deep learning approaches. So then you can expect better performance. So that is how you have to decide depending on whether your data is low resource data or rich resource data. Depending on that, you have to choose. And maybe the sentiment classification, so that what kind of model. So I am just giving one kind of machine learning model, then we'll see different deep learning algorithms. So of course I am just stating the problem. What is the problem here? So given one document, that is one review which is stated in the document D, and of course there are some set classes, sentiment classes. Maybe there are K classes. Assume there's a multi-class sentiment classification, the moderate level. There are some K classes. Then, so you will be having some training data where every document is labeled. So the training data is given to you. So where that is D1, the document 1, that is the review 1, is actually assigned to the class 1, so on and so forth. So that is how the documents are available. The last document is assigned to some kth class, something like that. So that is how the labels are, the training data is available. And what is our objective here? The objective is given a new document, new test document or test review, we would like to predict, so like whether it is like the class of the review. So whether it is belonging to, the class 1, class 2, class K, something like that. So that's the objective. Then you can use any of the machine learning models, of course, but the most important, the most successful model, the successful machine learning model for the document classification is the naive-Bayes algorithm. Why naive-Bayes is, only thing is, if you consider the features are independent in your document. That is where we are moving forward and using the naive-Bayes algorithm. Yeah, so maybe the mathematics of it also I have given here. So you can see, assume that your document is represented with, we have seen how to get the features out of it, right? So assume that the document D is represented with the features, the feature 1, feature 2, maybe the n-dimensional feature representation I am using to represent my single review or the single document. And so how do we predict using the naive-Bayes or the Bayes classifier? So what is your Bayes classifier? What is the mathematical expression we use? We assign the document, the given document to D to the maximum posterior probability class. Is it not? We identify the posterior probability to every class. Right? The document is given, what is the posterior probability for the first class, second class and kth class. Then to whichever class it is having the maximum, to that class will be assigning. So that's what the rule will be following. And of course, how do we compute that posterior probability? Probability of the class given the document. That's what the posterior probability, and that can be written as the likelihood into the prior probability, right? Because the bottom part is the same. That is how I have omitted that, the denominator, and I have considered the posterior probability is converted to the likelihood into the prior probability. And the likelihood can be written as, can you see the probability of D given C is written as the feature vector. The document is now represented as the feature vector F1 to Fn given the class, right? But we know that there is an assumption. So your features are independent. Every feature is independent in your document. That is where we can consider naive-Bayes. Rather than considering the normal Bayes classification, we can consider the naive-Bayes algorithm. So now instead of writing it as joint probability, we are going to write it as probability of F1 given C into probability of F2 given C, the feature, individual feature likelihood we are finding out. So that is where it becomes the naive-Bayes rather than considering the Bayes classification. So now the class, the predicted class is equal to the argmax of the prior into the product of individual likelihoods, right? So it boils down to the last equation now. Your document classification is equal to the posterior probability. So the argmax of the prior probability into the product of the individual likelihoods. So that is how you can.
So feature wise also we are calculating the probability of the class as well as the position.
Feature wise we are considering. So that is where that becomes a naive-Bayes. That's the difference between Bayes and naive-Bayes, right? So in case of Bayes we consider it as like feature vector. So now when you have the independent features, if you consider the covariance matrix, so the covariance matrix is independent, the features are independent, you will be getting the diagonal matrix. The off diagonal will be 0. So then your covariance matrix, the parameters you are predicting will be very less. Only the diagonal parameters you need to estimate in your covariance matrix. So that is how it is advantageous. Yeah. So maybe one example I am showing is straightforward, you can take it. So we are running out of time. So.
Sir, ma'am, we just, that's it. 2 minutes can you?
Yeah, okay. So now here you can see the training data and the test data we have. So both the negative and the positive, right? And we are going, that's the training data. I just have taken some synthetic miniature data set I have created. 3 documents in negative and 2 documents in positive, right? And then the test document I have, is given to us. We need to predict whether it's belonging to positive or negative sentiment. That's what we are going to predict. That's a document. Assume that it's a document, okay? Predictable with no fun. So that is the review that is given to us. We are going to predict it. So now you can see the prior probabilities. What is our naive-Bayes expression? So it's argmax P of C into the product of this. What is P of C there? There's a prior probability. How do we compute the prior probability? The class, how many examples are belonging in your training data, how many examples are belonging to the positive and how many examples are belonging to the negative. So that is where your P of minus is like 3 by 5 and P of plus is 2 by 5. So then we need to consider, so those two are like the posterior probabilities. The posterior for the positive and posterior for the negative. So how do we get the posterior for the positive and negative? The prior probability for the negative class into the likelihood for the negative class for the entire sentence. So the sentence given the negative class. That's a likelihood for the entire sentence for the negative class, towards the negative class. And we have got the value. And similarly, the prior probability of the positive class, the below line, the left, the right side to you. The positive class prior probability, already we have the 2 by 5 into, and the posterior, the likelihood of the sentence, that is the entire sentence given towards the positive class. That's what we are computing. And how do we compute this? Probability of S given negative, and that is the sentence given the negative and the positive, every word. So you take every word and what is the probability that the example is belonging to the positive and negative. So that is how you compute and take the product of it. Then, so to whichever class it is maximum, to that class you assign that. That's how you can. So then the deep learning, of course, the hot favorite, the deep learning algorithms. So machine learning models kind of, so they are outdated, like performance wise they are no more in competition. So that is where we need to have the deep learning algorithms, of course. So you can very well use the regular dense neural network algorithms, right? If you observe the dense neural network algorithms where your input is a layer, a dense input layer, then few dense layers, an output layer. So if your sentiment classification, there are 5 classes in your sentiment classification, then make your neural network the 5 neurons at the output layer, and input layer will be the size of your feature vector. If your sentence is represented with something like 1000 feature vector, then 1000 dimensions should be at the input layer and hidden. So it's regular, right? But the problem is here again, so of course it learns the features, so what you call it. So it learns the hierarchical features. But the problem is, so again, so you have to pass the entire sentence. Is it not? Entire sentence you have to pass at the input layer. And it cannot extract any ordering in the data. Either you have to use a TF-IDF or what you call it as the bag of words representation or one-hot encoding. Such kind of representations you have to use.
Very basic question. These are ultimately some neurons are working within the hidden layers, right?
Yeah.
And the factors of number of neurons should be present in a hidden layer is up to us.
Yes, of course. But usually, according to the research, so like if you design this kind of model, that gives you better result. So maybe if you assume that the input layer is something like 1000, so better increase to the next level. So that non-linear, like you are moving your features to the non-linear space or the higher space. So usually in the higher space, so the features will become more separable in the higher dimensional space. So actually you are doing that, right? You are learning the features. So in the higher dimensional space. So that is why the diagram is also taken like, so 3 in the input layer and 4 at the hidden layer. It's like go into the higher dimension, then you come down because the output layer is again like 5 or 10 depending on the number of classes. Again you should come to the lower dimension space when it comes to the classes. So of course I am not going into the details of it because it's very basic, I assume. So the problem here is these neural networks, of course I'll come back to that. The basic deep neural network, like only the dense layers, the network with only dense layers. So you had to pass the entire sentence, remember, and all the sentences should be of the equal size, is it not? Your feature vectors, like you should assume that all the sentences of equal length, then only you can use this kind of networks. Yeah, have that in mind. And then we are going to use a convolutional neural network. People feel that with text we cannot use convolutional neural network. That is wrong actually. You can use convolutional neural networks also once you formulate that kind of grid structure. Yeah. Here what I am showing is for every word, so maybe you can use any of the GLOR embeddings or ELMO embeddings or BERT embeddings. You get the embeddings. So now you formulate a matrix with that embeddings. So say for example, my review is having all the words. Not going to the beach tomorrow. Right? Is it increased voice? Or I am getting echo or what?
No.
Is it fine?
Yeah, fine.
Okay.
I think that sensitive.
Oh, okay. Fine.
Can I just
Okay. So you have to formulate the grid kind of structure. So because CNN actually works with a spatial dimension, right? So though there is no spatial data, so you formulate such that there is like spatial structure, the grid structure. Then you can pass it to your convolutional neural network. You can apply any number of layers. You can have the convolutional filters. So then they will be extracting the data from it. So do you observe how do we formulate that kind of grid structure, and then how we can formulate a single two-dimensional grid with all our features. So like for the word not, so I have taken the feature vector, and then for going I have taken another feature vector. Please observe that here we are passing the word level feature vectors, and here we have to pass the sentence level feature vectors. Please observe that every input, every document is different. Is it not here? Every document we are making it as a feature. That is, every review we are making it as a feature. That is the entire review, and then we are processing it and we are getting the output. And one input, like every output is dependent on the previous and the future outputs. That's a problem here. So now we are making the words, so into the feature vectors, word level features we are taking, and maybe the learned features you can now extract. All the pre-trained models you can use, either BERT or ELMO or GLUR, whatever it is. So those features you can take, and then so you can formulate your CNN of your interest. You can have your dropout layers, your what you call the patch normalization layers, or maybe the pooling layers. All the interesting stuff you can use in your CNNs, and then at the end you use your dense layer so that it will be useful for the classification task. So in the convolutional layers, all the features will be extracted, all the required features, and at the end you can formulate your dense layers. So dense layers are responsible for the classification, and finally have a softmax layer, so which is equivalent to the number of neurons equal to the number of classes, so that you are getting the class-wise probabilities, the probability distribution for the classes. Fine, that's how you can use the CNNs. Again, I am not going into the CNNs because it's not a computer vision related topic. Fine, yeah, but still you can use it. So then, yeah, so here I am talking about the problems with the DNN, the dense neural network. So they don't have any memory, and every output is independent of the future, the past and the future inputs. That's a problem, and every document should be of the equal length. Then only these networks work. That's the problem. So and these models cannot be used to predict the next word. That is the problem. So that is where we are going for what we call it as the recurrent neural networks. The RNNs, so which have the memory, right? So the recurrent neural network, which have the capability of, a variant of the feed-forward neural network again, but they have the capability of memorizing it, and they can work, they are capable to work with varying length sequences. That is the most important thing we need to understand. And they can preserve the ordering also. So that is the advantage of using the RNNs. So here you can see the same kind of neural network, but we are, we are rotating in the anti-clockwise direction so that we get that kind of structure. So one state output is fed as input to the next state. So that is how the recurrent connection has been established. That is what the recurrent neural networks are. And maybe if you unfold that, you can see this kind of unrolled or unfolded version of the RNNs. So you can see that kind of representation. So at every state you are passing one word. So you can see the X, here you are passing X1 is the first word, maybe the X2 is the second word. The yellow ones are the inputs now. They are the words, individual words you are passing. So every word you are passing, and at every state your network is doing the same thing exactly. That is where, if you observe, the W, U and V, they are all the shareable parameters. Can you see? The W is shared across all the states, and your U is also shared. Now, though your network is extended to 2000 states, your parameters will not be changing. The same old U and W you are using, and of course V also. And depending on the task, your network outputs can be considered or can be ignored. right? So this is what the recurrent neural network. Again, the basic stuff I am not going into the detail. So then, because the recurrent neural networks are having some limitations, they cannot, they cannot be suitable. They are not suitable for the long-term dependencies. That is where the long short-term networks, the long short-term memory networks have been introduced, and which are designed with 5 gates: the input gate, output gate, the forget gate, this input cell, and the hidden state and the context cell. So that is how the LSTM networks are capable of storing the long-term dependencies. So maybe in RNN what happens is, if you extend this for 1000 states, the first state data may be ignored. So that is a problem with RNNs. So that is where the context state has been introduced into LSTMs. That is where it is capable of memorizing the long short term. What has to be memorized and what has to be forgotten, that can be easily learned by our LSTMs. So I am presenting a lecture now. You know what has to be remembered and what has to be forgotten, is it not? And tomorrow we are waking up and we will, do you remember everything whatever you are seeing in the real world? No, right? We know what to remember and what to be forgotten. Like that, LSTMs also at every state, what has to be remembered and what has to be forgotten, they can understand that. They are capable, that is how they are designed. And here you can see, I am showing you, so how this LSTMs can be used for the sentiment analysis task. So you can see different states. At every state, we are passing one word. And the words are not directly passed, they have to be first converted to the embeddings. So embedding corresponding to that word we are passing. So that word embedding, of course, the dimensionality is just synthetic, d equal to 4. So that the word embedding we are passing, and at every state we are passing like one word, and it can be extended to any number of states also. But the parameters will not change. In case of the dense network, what happens is, if you increase the number of layers, your number of parameters will grow like hell. That's a problem. The complexity will grow high. That's the problem. So that is addressed in case of the LSTMs. Of course, these are also not less, but still, so even if you increase the number of states, the parameters will not be increased. That is how they are designed. And because it's a sentiment analysis task, you can see, I am not interested in the output at every state. Here you can see basically RNNs produce one output at every state. You can see, you can observe that. But I am not interested to do that. So here maybe this kind of network is useful for something like named entity recognition or parts of speech tagging, where every word should produce one output, right? So a named entity recognition, every word should be given, either it is a organization or a place or a name, that is what we need to recognize. Or in parts of speech tagging, every word we should say whether it is belonging to the verb or article or whatever, what kind of parts of speech it is. In that case, this kind of network is required, where every state is producing some output, so corresponding to the input. But in case of sentiment analysis, I don't need that. What I need only, after passing the entire text, whether it is belonging to the positive or negative, or to which class it is belonging to. Maybe that among the 10 classes, to which class it is suitable, that is what I need to. Then I am ignoring the output from every state at the initial states, and whatever I am getting the last state, that output I am passing to another deep neural network. Maybe you can see there is again another dense layer you can use. There is a neural network representation layer, right? Yeah. So that neural network layer could be a dense layer, and then after that you can have the softmax layer that can be extended to any number of layers depending on your complexity again. Then finally you are getting the class, the sentiment class related to your text. The entire text is processed, and here you can observe. So in case of the DNN, you are passing the entire sentence. Is it not? The left side, the dense network, entire sentence you are passing, and you could not preserve any dependency in your words. But whereas in this case, when I am passing to the LSTMs, so that is the first word, there is a second word. And the second word is getting some feedback from the first word also. The ordering you are preserving, right? And when you reach the last state, you are getting the essence of the entire text,
Yes.
right? All the feedback you are getting and what has to be forgotten, what has to be remembered, the LSTM knows very well with the 5 gates that are inside the LSTM cell. And finally we are getting the gist of that in the last state of the LSTM cell, and then you are passing it to the softmax layer, and then you are getting the classification output. So that is how the LSTM, the recurrent neural networks, can be used for the sentiment analysis task. They work very well. And of course, if you are interested, you can extend that to the attention mechanism also. So here, so maybe for the classification task, all the words that you are giving equal importance, right? So that is where, of course, I'll not go into the details of attention now. Maybe in the machine translation part, I'll be explaining about the attention. So here, maybe some words are very, very important. So here, if you observe, so all the words are not important for my classification task. Maybe some of the words, say something like, the product is wonderful. So the iPhone's camera is too good and it's heavyweight. Both are there maybe. So in that, maybe it is in the training data, it is given as positive review or maybe level 4. In that case, which are very important there, heavyweight, those 2 words important, and it's awesome or great. Those words are much important. So why should I give equal importance to all the words? Can I give different importances to different words? That is where, and also one more thing is, so you are taking only the output of the last state, and by the time you reach the last state, maybe you are losing a lot of information. So the first state's information, maybe it is not possible to, for the LSTM also to remember. That is where, so you are passing, the linear combination of all the cells outputs you are taking before you pass it to the softmax layer. Can you observe that, the difference between the previous one? The previous one, you are capturing, like at every state you are passing one word, capturing some information, and you are passing to the next level. And the last state information alone you are capturing and you are passing to the softmax layer in this case. But here in this case, so rather than doing that, you are taking the linear combination of all the output states, where every word, every state you are passing one word, right? So every word essence you are getting, and the last state it has essence of all the dependencies, and then you are taking linear combination of it. And for that, maybe if you would like to have different weights for different states, you can use a new an MLP, the multi-layer perceptron, where it could be of different weights also. So that in detail I'll explain in the machine translation lecture. So
sometimes people, LSTM is one directional, right?
Bidirectional also you can have.
So
Bidirectional also you can have. The problem is sometimes, especially in the language generation task, in that task, or auto completion task, what happens is, maybe depending on the future word, my current word is predicted. Current word is dependent. In that case, if I see only in this direction, so it may not be correctly predicted, right? So in that case, the future and past both together, if I use, then my prediction of the current word would be better. In that case, we use the bidirectional LSTMs. Even for these tasks also, we can very well use it. Of course, I have not included. Maybe in the machine translation, I have used it. You can use it. So that's about the attention mechanism in the sentiment analysis. And so far we have seen all the stages of sentiment analysis. So we have seen what sentiment analysis, what are the applications, what is the motivation. Then we have seen how to collect, what are the issues we need to address in collection of the data. Then we have seen the pre-processing stages. Then we have seen feature engineering especially. So like different feature extraction techniques and different models. So like the machine learning models and the deep learning models we have seen, and once we are done with that, how to evaluate the model. And of course, it could be intrinsic evaluation and the extrinsic evaluation. Intrinsic evaluation means maybe you can use, because sentiment analysis, it's after all a classification task, you can use the precision, recall, accuracy, AUC score. So generic, like we all know about that. So any of these scores we can use it. Otherwise you can use the, like if you are, because we are in the academic research, we prefer using the intrinsic evaluation only. So one of the validation, like part of the training data, we use it for the validation, and then we report the accuracy in our, while writing the papers and thesis and all, right? Otherwise, when you are working with a product, real-time product, then it is very much important to work with the real-time, after deployment, how the accuracy, how the performance is. So that kind of evaluation, we call it as a extrinsic evaluation. Sorry. Yeah. So then the next application, the machine learning, machine translation. So what this machine translation is, and of course, so I'll be focusing more on the models here because we already discussed a lot about the NLP and the challenges. So again, the challenges will be the same, so I'll not be focusing on that, I'll be focusing most on the modeling part. Yeah. So the machine translation, what it is? What is machine translation? So the task of, so translation of one language or transforming source language to the target language, we call it as a machine translation. And of course, human translators used to do that, but the problem is if the machine can do it, it will be wonderful. Maybe I go to Germany or Japan, so nobody knows English there, that's a problem. So I cannot enjoy my stay there. Then what I can do, maybe I can use a machine translator, like automated translator, and then I can use it. So that is a great application, right? So already you must have used it, your Google Translator. So the same thing. But how to implement that? What are the issues? What kind of models? Being in the academics, so we need to understand all that, right? Yeah. So of course I have shown some examples like Telugu sentences translated to English so that every one of us can understand what the model is doing. Yeah, one more thing is like while developing these models, we are expecting a model with little involvement of the humans. Either maybe in the pre-processing stage or at the post-editing stage, we are expecting the human involvement, but we are not expecting the humans to involve in between the model development stage. So that is another important thing we need to understand. Yeah, what are the challenges? Of course, I have already discussed about all these challenges, right? So at the beginning and sentiment analysis. So I am not going into the details. Maybe you can. I have just listed down just for your convenience, and you can see. So what Google translated for me today. We need a table for 5 people. What is the meaning of it? Maybe I have gone to the restaurant and they said I would like to have a table for 5 people, right? But what is the translator doing? Now of course Telugu, but what it is doing? What is it saying? Aiduguriki pattika kavali. Table has different meanings, right? Table has like this table, yeah, not this table, this table also, like data, we formulate in the table format. That's what the table. So it got confused. So it is saying, Aidu mandiki pattika kavali. So it's a bad translation. So still, till today, the top-notch translator, the so-called Google translator is not doing good, right? Yeah, that is where we need to contribute for the development of these models. Yeah, so maybe we need to use we need to understand the ambiguities at different levels. So at the syntax levels, at the structure of the language we need to understand, especially we are working with different languages now. So earlier sentiment analysis, at least we are dealing with a single language, but here it's different languages. Maybe English to Urdu language translation. I need to understand the English language and also the Urdu language, at least the structure. So maybe some languages are following something like subject, verb, object form, and some other languages are following subject, object, verb format, right? The structure of the language we need to understand. So the syntax of the language, the semantics, that is the meaning of the language, maybe the same word is having different meanings in different languages, that is possible, right? Yeah. So that is where we need to understand the semantics of the language also, and the pragmatics of the language, and the world knowledge means the common sense. So the model is expected to have some common sense. I have shown some examples where it is required. Cat is flying, so is it possible for the cat to fly? So such kind of common sense is also important. So this is where the ambiguity resolving is important. And what are the approaches that we can follow for this machine translator? So when we are developing the machine translator, so we can use any of these approaches. So since the beginning, it's not new actually. So it is before 1947 itself, these models are available. So you can have the template matching approaches where, maybe we are, maybe we are translating from Telugu to English. So now we will be formulating a template based approach. So the subject, object, verb form. So the subject and object will be converted directly. Maybe the names and all, they are converted directly, and then in between there will be blanks. So we will be filling the, we are using the machine to fill the blanks. So that was the earlier approach. So that was a template matching approaches, we call them as. And then of course the rule-based approaches, and under the rule-based approaches again there are something like transfer-based approaches, transfer-based machine translation approaches, and the interlingua. So now the language, so source language, target language. The source language is in turn will be translated into some abstract representation, and that abstract representation will be converted to the target language abstract. Then the target language abstract will be again converted to the detailed representation. So such kind of approaches were available around before 2000s and all. So those models were not that good actually. So that's a problem with these approaches, the rule-based approaches. You are kind of writing the rules for developing these algorithms. Then came the statistical machine learning algorithms. When data started flowing around, so then they started working on the statistical models for the machine translation approaches. And then of course recent, after the introduction, so the neural machine translation. So that is, you are using the neural network models for the machine translation. So that is what the neural machine translation is. Neural network based machine translation. Yeah, see like when to use what, or like if you consider the architectures, the direct translation approaches, the template matching approaches, then the rule-based translation approaches, the second generation. If you observe, so first generation is very bad of course. The second generation, they were very good, but so if the languages are very close, maybe Hindu and Urdu, if you consider they are close, is there any closeness? I don't know. Must be, right? Yeah, I assume. So in such kind of languages, you can use the rule-based languages, right?
No, ma'am, whoever doesn't know Urdu, they feel that Hindi and Urdu are
that's what, because I don't know, so I am assuming
that.
that.
Actually.
Okay, fine. I don't know. Of course.
So almost same.
Like inherited.
Inherited.
Yeah.
Yes, sir. Hindi is.
So for Dravidian languages, Sanskrit is a root language, right? Dravidian languages. So like all the most of the Indian languages. So the root is the Sanskrit. So Telugu, Tamil, sort of Dravidian languages. So maybe few languages are like similar in nature.
All the Dakkanese languages which are being spoken are from
Sanskrit. So that is why. So if there is more similarity in the languages, then you can use this rule-based languages like transfer-based approaches or the interlingua. So kind of, because the abstract you are creating and it's close. So that is how they are useful. But so when the languages are entirely different, maybe it is something like Telugu and French. They are entirely different. The semantics are different, the syntax is different, the structure is different, entirely they are different. So in that case, so none of the first and second generation algorithms fail, like they don't work. So that is why we need to go for the advanced approaches. That's a third generation, that's a neural machine translation approaches we need to use. So of course, they work better, but what they expect is huge amounts of data because you are making use of your deep neural network algorithms. Of course, the good old neural network algorithms you can use. Of course, the dense network you cannot not use it. Don't think that we are using dense neural network. But so once you have, like, if you have enough computational resources and enough data available in both source language and both target language. Remember, so like you should have the source language, the associated target language also. Then only you can apply the machine translation training. So you can submit it to the machine translation model. So of course, does it work always better means it need not be. Like there are very low resource languages. So for that, like low resource means we don't have enough data sets like Urdu and all. So we have never worked on that.
Parallel corpuses are there to train the
yes. So only for those models. Even if you have large data sets also, it need not to work. That's a problem. So if you consider German language, so German doesn't use any space in between, They don't use any separator. That's the issue with German. So that's a problem. So there are many complexities we need to understand. Of course, I haven't gone through the details of languages and all. So linguistics we need to understand. So it need not to work. So when to use it? Of course, when you have a lot of data and a lot of computational resources and like associated parallel data you need to have, then you can. And what is the neural machine translation? So you are using like deep neural networks for the machine translation. That is what the neural machine translation is. And what is the problem? So I am just stating the problem here. What are you doing here? So you are going to find the target sentence, given the source sentence. That is, you are, like in terms of the probability if you consider, so you can pose it as a probability problem, right? So like conditional probability. So you have to identify the y given your x, and for whichever y it is maximum given the x is a set of words and y is again the sequence of, like both are sequence of words only. So for whichever the probability is maximum, so that kind of y you need to generate. So in terms of course, so it is very much important for us to understand the mathematics behind it. So that is what the problem statement is, right? R max of y given x. So y is a sequence of words, x is a sequence of words, and whichever sequence of words give the highest probability that is suitable for the given sequence of words x. So that kind of words, sequence of words we need to represent. And of course, so why neural machine translation? Why not the transfer based approaches and all? Because so they are capable of generative models. So they can generate like sentences which are not in the training data also. So when you are giving the training, maybe you are giving the sentences in different words. Maybe I am presenting a class, I am presenting a class on NLP, I am presenting a class on something like machine translation. So these kind of words are given. But still your model, so which is suitable for some other text, so maybe it can generate mixing up all these three sentences also. So that is the capability of the neural networks. So that is where they are more efficient compared to the other kinds of approaches. And if you consider not the regular models, the regular deep neural networks, that is this kind of deep neural network is not suitable. The models that are suitable we call it as encoder-decoder models. So the encoder, like there should be an encoder and there should be a decoder. So that is what is much important. And of course, what are these encoder-decoder models? So we'll be using, of course, in this case, we are using the encoder, the recurrent neural network as the encoder and the recurrent neural network as a decoder, right? So you are passing the source language sentence as input and there is a recurrent neural network. Of course, there will be different, states and all. So that is the recurrent neural network. That part is an encoder, and so there will be the feature. The context vector. The encoder will be encoding the given sentence. The encoder recurrent network will be encoding the given source language sentence into the context vector, and that context vector will be the input to the decoder. So the second recurrent neural network that will handle this context vector and will convert that to the target language. So that is how it is, designed. So this kind of encoder-decoder model is designed, will be used for the machine translation. Maybe here.
For multilingual.
Multilingual.
So
then
we are
it
actually
should be
splitting
this here. So this context vector should be passed to another decoder. Two decoders will be there. Here, this part is one decoder, this part is an encoder, and this is a context vector. There's a connection between your encoder and decoder. When you are working with multilingual, then there should be whether source is multiple or target is multiple. That depends, right? So usually target is multiple. There is something like, so take the multiple inputs, source languages, and multiple prediction is also multiple. That is also there. That is also possible. You can have multiple encoders.
that comes under actually back translation.
No. Back translation is an approach where you are kind of augmenting your data. Text data augmentation technique that is. Usually what we do in case of image augmentation, you must have seen.
Yes.
What is that image augmentation we do? We do the cropping, is it not? We do the cropping, we do the zoom in, zoom out, maybe translation, rotation, scaling, all that we do. In case of the visual data, we can do all that. We can see that also. But in case of the text data, that is not meaningful. Maybe what we can do is masking we can do. Maybe masked encoder also you can design actually. That's one interesting area. What you can do is, so like self-supervised learning for that you can use. In the given source sentence, you just remove one of the word, but still you are expecting your model to generate the full sentence. So then your context vector is strong. So that with your noisy data also, your model will be working. That's an interesting research problem. Masked autoencoder, you can refer to that. Masked autoencoder. And back translation is an approach where it is for generating the augmented versions of your text. So you have limited data, like low resource data. Then you would like to augment it. Then the one technique is like this, or you can use the back translation approach. You have generated, you have designed a model, you have generated it, and use that model to back translate it. So that is how you are getting the data. That is what the back translation approach. So now let's see the working of the encoder decoder models. I have the encoder. What the encoder decoder models are doing? We are going into the details. I just have shown this the encoder decoder models, right? So encoder is recurrent neural network, decoder is recurrent neural network. Because LSTMs are better, we use the LSTMs. And now we are going to use the encoder part. This is how the encoder is designed. A simple LSTM, right? Or you can use the RNN also, or GRU also you can use. So the source language sentence we are passing as input, and we are getting the states. At every state we are getting the output, right? And I am not interested at the output of every state, right? Here I don't want to get the output at every state. I am interested to generate, after seeing my entire sentence, then only generate the new sentence. Is it not? So that is why, so I am not interested to get any output at every state. So I am going to connect to this to the what you call the decoder. So now let's see the decoder part. So now you can see, so that S0 is the output of the last state of your encoder. So this is the output of the last state of the encoder. So that is what the starting state for your decoder actually. So here you don't have any initialization for your encoder. That's randomly you can pass it. But what we do here is, so this output of the last state of the encoder will become the starting state for your decoder. So this gets actually the gist of your entire, encoder. So that is entire input sequence, the source language. And also that we call it as a context vector also. Because, so that have the context of the entire source language. And this will be connected to your, what you call the decoder. Now let's see the decoder. Yeah, actually both are the same. Why am I dividing into C and S0? I'll show that later. You can understand later. So you can see that. So S0 is the input to the decoder, the starting state of your decoder, and also the context vector. And the next state. If you observe the next state, what is the input to the next state? S1 is the next state. S1 is the input to the next state, right? To the S2 in decoder. And also the context vector is the input. That is one way of doing it, so that your predictions will be better. So usually what we do is, this context vector will be the input here, and then only this line will be having. But rather than doing that, so we are intelligently doing it. At every state, the context vector will become the input while predicting every word, so that your predictions will be better. That is how we generated this model. Please try to understand that.
This what is that you are giving them?
1 second.
Not here.
No, I'll just go back and show you. So here actually, this is the encoder part and this is the decoder part, right? So the encoder last state will be connected to the decoder first state. That's the only thing we do. And whatever we are connecting, that's what we call it as a context vector, because it has the context of the entire source language, right? And this is one approach. Of course, in both the states, here it is an LSTM, here it is an LSTM. So that is how we design. But the problem is, so because the context of the entire input sequence is passed only at the input layer, at the first state of your decoder, maybe while generating the last word, you are losing some information. Is it not? So what we are doing, what I have tried to do is, I have passed the context vector to every state. So that while generating every word, my context vector will be available. So that even my sentences are lengthy, I'll be getting better predictions. So with that intent, I have done that. So I have shown, what I have shown is a different version actually. So here you can see S0 and C. S0 is the input to your decoder and C will not be there actually. But now I have changed the model, actual model. So C is passed as input to every state of your decoder. So you must be cursing, all of you are hungry. Yeah.
Full hungry.
So this is how you can design your encoder and decoder. Okay.
You can wind up in 5 minutes.
Yeah, of course. I'm almost done. 5 minutes. Madam, please ask your doubt. Madam, you asked me doubt.
Madam was asking that's why.
I forgot.
Why not and why one? Why
Now
not?
I understood why, what is why not.
Why not is not. Why one is the output, right?
Yes.
The target language first word, target language second word,
That we
and
are
so on.
getting, ma'am. That we are getting, but again to this decoder, we are giving context vector. Again we are giving this target language corpus also we are giving. As an input to the decoder.
No, while training we do that.
Acha, why training?
That is what we call it as teacher-based learning.
Acha.
Because in training, maybe this word predicted is bad. Then what happens? The entire sequence will go back, right?
Yes.
That is how, while training, we ensure that. So rather than considering this, the word that is predicted by the decoder, we pass this actual targets also we have in training. The
Yes.
actual training targets will pass it.
Yes.
So that kind of training we call it as a teacher-based training. So actually we have that. So that is what we are utilizing. Otherwise the target language sentences are not useful for training. You got the point now? Yeah.
Yes.
So that is why we are using.
Ma'am, with this y1, y2 also certain context vector is also generated. No? There is a context vector of one.
So this y values, hidden state you are getting, right? After hidden state, we are using a softmax layer at every state. Of course, these are all different states only. Unrolled version of LSTM I am showing. So at every state you have the same thing. So you have the hidden state as output, and that hidden state will be passed to softmax layer. That is where you are getting like maybe your vocabulary is 50,000, your softmax layer will be 50,000. So that is where I am getting one of the like Rmax probability, the probability vector I am getting. Out of that I get the maximum probability word. That becomes my correct, like the predicted word.
Yes. Right? Probability playing great.
Yeah, it's a probability distribution. That is how I have posed it as a probability only. So while posing also I have posed it as probability. That's what more important. So yeah, I am showing that the probability of the probability of y given x is actually, we are approximating that, right? So we should get the sequence of words in the target sentence which are most probable or the most suitable for the given source sentence. That is what the R max probability of y given x we have seen. And then how do we get this like probability of y? Probability y is the prior. If it is like when we are considering the joint probability, the conditional probability. So the posterior probability. So this is the prior probability, and how do we get like yt? What is yt? Yt is the teeth state. The word that is predicted is the teeth state. It is depending on all the past states outputs, right? And also the context vector. Whatever is the maximum probability word that is decided depending given all the past words and also the current context vector. So that is the word that you are going to generate. This is in terms of the probability, and this we are achieving with the help of our recurrent neural network. If you observe the softmax layer, the recurrent neural network actually it's not touch. Yeah. What we are doing here? This yt. So this yt, maybe if you assume this is a teeth state, what is this yt? This should be the best word, the suitable word, given this previous two words, right? These two words, and the context vector also.
Yes,
Got the
yes.
point now?
Yes.
So that is what we are predicting now. So without using the probability, we are designing it actually, and this LSTM is doing that job. The probability, the highest probability word, it is predicting. Yeah. So now, like LSTM, if you do the encoder, if you consider the encoder decoder, you can see here that the context vector is actually is the connection between your encoder and decoder. Can you see that? And the decoder, of course, I have modified for your understanding, but usually this is the case. So the encoder is producing some context vector, that is the essence of your source language, and that will work as input to your decoder model. And so the problem here with this kind of encoder-decoder representation where the context vector is connected, the problem is if your sequence, if you assume that the sequence, the number of sequences or the number of words in your source or target is some 1000, then so maybe while producing, so assume that there are some 1000 words in your production. Then by the time I reach 100th word itself, my context is lost. Is it not? That is where I have given some field with a context vector for every state. Do you understand now why I have done that? Yeah. And also, even if I pass it, of course, this I skipped because I am already explaining it. You can read it for your understanding. So what we can do is, so rather than considering this kind of, so this is an encoder decoder model we have seen earlier, and now we are going to take whatever I have shown in the sentiment analysis task. The same thing I am doing, but there only the one output. But here I am doing, I am having that at every state. So now the encoder part, every output of the encoder state I am taking, and that will be taken as a linear sum, and that will be fed as input to every state. Got the point? And what is your context vector? Here, what is your CT? Here it is CT, right? What is your CT? Only the last state of your encoder. That is a CT, and that will be input your the first state. Even if I pass it to the CT also, so that will be the last state's data only, right? The modified version I have shown. But here what we are doing, I have taken all the hidden states output and I am formulating my context vector as a linear combination of, can you see that? All the HIs. What are these HIs? The hidden states produced by every state of your encoder. Can you see that? So it's a linear combination, but I am not using different weights. Maybe I am giving equal weightage to all the hidden states. Now can you see, even if your encoder is having 1000 states, so I am getting the gist of all the states. Please observe that. Here, so if it is too lengthy, maybe the context vector contains only the last information. It is not having the prior information. Maybe most of it you are losing, right? So to avoid that, we are taking like the output of every hidden state, take the linear combination of it and pass it to every state as a context vector. So that you are not losing much information from your encoder. And then maybe here I am giving equal weightage, though I am giving different, so like all the encoders input, like outputs as a single entity, the context vector, but it's not like uneven information. So why should we go for the attention? So there's a motivation for that. Here you can see, so it's a English to Spanish translation. I love coffee, me gusta el café. So that's the Spanish translation. So now here, maybe the way I'm talking may not be Spanish, okay? But whatever. So now you can see here.
But it is sounding
so like,
very good.
that's like, yeah, I've been to Sri Lanka once. Costa, so I made that. So like me, here it is me. So while predicting this target language me, this is like from I should have like highest dependency, right? So from I, this me word is like predicted, is it not? So in the earlier case I have shown, yeah, here you can, not here, yeah, here you can see, so like all the hidden states outputs are given equal weightage. But rather than doing that, can we have different weightages, uneven weightages of the, like by designing the context vector? That's what the question. Why should we have that is, maybe while predicting every word, I need not to have all the words. I have, this me is dependent mostly on I and very little on love and coffee. Is it not? And the same is applicable for the remaining words also. So you can observe the distribution, the dependency distribution of the words. So while generating gusta, then it is dependent on the word. Mostly it is dependent on love, right? And of course, little bit on the remaining words also. That is where, is it not like while predicting a word, so we should consider like uneven dependencies of the outputs of the encoder states. That is where the attention was introduced. And similarly, the same case is true with the remaining words also. You can see that here. Yeah. Here what we are doing, we are taking the outputs from every hidden state of the encoder and not the equal weightage. We are going to give uneven weightage for every hidden state of the output of the encoder. Yeah. Now now, can you see here, what is my context vector now? My context vector is, it's no more summation over HI alone. It's summation over alpha Ti into HI. What is this alpha Ti? It's actually different values. Here you can see alpha Ti, summation is 1. It's like softmax probabilities we are taking. We assume that's probabilities. All the probabilities together it should sum up to 1. And so it's between 0 and 1. So that's a probability value. And so maybe while predicting this word, this word Y1, this Chinese word we are predicting. While predicting this word, so it is having the context, we are designing the context. You see, at every state we are passing the context. And the context also, how it is designed as a linear combination of all these. And now, it's not giving equal weightage to all the words. Maybe while predicting this word is having higher priority. Then, this word should be having the highest probability. Maybe 0.8 here, 0.1, 0.1, something like that. Right? So that is how. Can you see that? Now, the context vector is dynamic now. The context vector. So one thing is the context vector is passed only to the starting state of the decoder, or maybe you can pass all the hidden states of the encoder as a linear combination you can pass, that is the other way, and the context vector is fed to every state of the decoder, that is the other way. And so rather than making the context vector a static context vector, make it as dynamic, so that it's having uneven distribution dependencies. So that is what the attention mechanism actually. Yeah. So why we are calling it as attention? Can you see that? While predicting Y1, maybe the first word X1 is having highest priority, is given the highest priority. The model is attending to that word mostly.
Yes.
Right? So attention is not uniform. Now certain words in the source language are given higher attention than the remaining words. So that is how you can call it as attention. So like maybe I give you this analogy. Attention, why we call it as attention? You are watching, right? You are opening your eyes and watching. Are you seeing the entire visual, whatever you are seeing, with equal priority or different priorities? Now you are watching. I can see, of course, all of you also. And mostly what am I focusing on? I am focusing on this and I am focusing on this. Is it not? So everything we see may not be given equal priority. Depending on what we are doing, so our priority will be, our attention will be different. Is it not? Right? Yeah. So that the same thing is applicable here also. The human attention, we also, like maybe I am reading a book. So while reading the book also, I can see of course the entire book. Even I can see like somebody is talking, I can hear that also. Is it not? That's what we do. But our attention is mostly on what we are doing. So the words I am reading, that is given highest priority. Then what I am seeing, the book is given the next priority, and the least priority should be given to the TV sound. Is it not? Yeah. So that is where attention is more important. Just like we humans, the machines are also expected to do. And of course, the variant of the attention, the soft attention, where we are giving different attention to different, what you call, the hidden states. That is different words. That's what the soft attention. Why we call it as soft attention? It's no more hard. So it's no more one, right? So in the earlier first case, it's a linear combination of all the feature vectors. In that case, so like if you consider 1 as the weightage, it's equal. Now it is no more hard, it's soft. So maybe you can some other time, or maybe you can refer to that based on my inputs. So this is the mathematical equations that are involved here. Okay, already I have taken,
So A1
Yeah.
is calculated.
This is how you can compute. So what is your context vector? Your context vector is dynamic now. So your context vector is a linear combination of all the hidden states of the encoder now. And what are those alphas actually? Alphas are the attention weights, attention scores. How do we get that attention score? Attention score again should be softmax probabilities, because all the attentions should be summed up to 1 and it should be between 0 to 1. To satisfy that criteria, we are using that softmax equation, and the EIJ are the outputs of the hidden states. Yeah, that visualizations, you can see the visualization also. So now you can see, so like while generating a word, which words are given the highest priority. So those words are shown with clear color, and which are not required, they are shown with black color.
So that's how, maybe again the global attention and the local attention, you can refer to the papers now, you can understand if you have this idea. The global attention and the local attention, so means like all the features you are considering or only part of it. So if you consider all, maybe if it is 1,000 states, then so your attention may not work. That is the problem. So take only the local attention, only few like K states you consider. So that's what the local attention.
Or namely
Yeah.
K, certain.
Yes, of course. The evaluation, the blue scores, you can use it, or Metier scores, all that, you can use it for the evaluation. Yeah, anyhow, I'm done with it. I don't want to get more cursors today. So this is like, if you consider source data, I'm just showing how the data have impact on your translation. You have the source, and that's the human generated text, and you can see if you have 1 times the data, then that is how, it's very bad, right? The data, so like the data matters, the size of the data. If you have 10 times the data, then you can see it's like improved. If you have 100 times the data, like maybe it's 100,000s of data, so then it's much better. It's thousands of times of the data. It's almost equal to the human translation. So that is how data have a lot of impact on your model performance. So the additional resources, if you are interested to study, maybe there's a textbook for NLP, you can go through it. Speech and Language Processing by Jurafsky. So that is the textbook you can, and Martin. So it's a wonderful textbook. You can go through like very basics, all the basics. And if you are interested to go through like all the, tools and all, so then you can go through like NLP with Python and Handbook of Natural Language Processing by Nitin. So these are the wonderful reference books additionally. And if you would like to have the data sets, so I just listed few of the data sets, the widely used data sets, DVPDR, then New York Times, then Reddit comments. These are all the data sets that are available when you would like to work with text. The Stack Overflow for question and answering, Stanford question and answering dataset, Squad dataset, and routers for text classification, and Wikipedia extraction like C, 66 GB. So I don't think we'll be having the resources for training such kind of data. So these are the conferences and journals you can refer to if you are interested to study like very good literature on NLP. So these are a few of the conferences and journals you can go through. Yeah, these are the tools like NLTK for pre-processing and all. Genesimo also a wonderful tool for pre-processing. And of course scikit-learn if you are working with machine learning algorithms, if you confine to machine learning. And TensorFlow, Keras is like little bit API kind of. It doesn't give you the handover details. So if you have to go with TensorFlow. And PyTorch is very good. Compared to TensorFlow, you get 1% or 2% improvement if you use PyTorch. And of course, if you would like to generate the datasets and all, you can use Hugging Face and Spacey for for pre-processing, and Stanford Core NLP. So these are the different tools that you can explore and learn things. Yeah. Thank you for giving me the opportunity. So thank you for patient learning, and sorry I have extended my time.
No, ma'am.
Yeah, I have taken beyond the time. Sorry for that. And it's open for questions.
Have any question?
They have not yet identified the problem for their research. So
Okay, that is good actually. So they have attended now. They can formulate. I hope I have given enough motivation for them.
Providing this workshop as a platform for them to
That is good.
analyze what are the various research issues and the challenges in the various areas.
Okay, nice. Thank you.
Yesterday also we had a session on computer vision. So what are the issues and challenges? Few might have got minds got ignited in certain ideas.
Yesterday, Monday.
In Hyderabad yesterday, 1 month ago yesterday.
Thank you so much, ma'am. I am Nusrat Fatima on behalf of Department of CS&IT, AICTE Training and Placement Cell, and on behalf of all the participants, I wholeheartedly thank you, madam, for traveling from your place just for giving us a wonderful lecture and learning. Thank you so much, ma'am, for visiting us. Thank you, one and all.
Thank you, ma'am.
Yeah,
for
actually,
covering
I
right
love to
from the
inform-
basic first word of NLP